this problem, please note that we are starting our coordinate system from this left hand end over here. So the horizontal axis is Z here, and the vertical one is Y, positive downward. So if we want to know the boundary conditions, because under this load the beam is likely to deflect, possibly something like this, okay? So we don't know what is this deflection or the rotation at this free end at the left, but we do know at the support conditions here we have got our displacement 0, and also the slope of this line at this point is also 0. So dy dz equal to 0 at this point. So that is happening at only at z equal to 12. So if we look at all these conditions, our second conditions here is correct. For this problem again, mostly the reflection is going to be something like this. So we know the deflection at z equal to 0 is 0 and z equal to L is 0. We don't know deflection and the slope at any other point really without doing further calculation. So this is the correct answer. So in this case, we know displacement at this right hand support over here is 0, and displacement at this point left hand support is given as support settlement of L over 15. So while combining these two, we could say at z equal to 0, y is L over 15, and at z equal to 3L over 4, y equal to 0. So this is the correct answer. For this problem, when you are doing the calculation, you probably have been given some numerical value for B and H, which you need to substitute, and also the thickness T you have been given. So the way you can approach this problem is you can think about this outside rectangle, for which the second moment of area about this axis xx would be bh cube over 12, where b is the dimension, outside dimension, and outside width, and h is the outside height. Now if you take away from this value the inner rectangle, which is here, which has got width as b minus twice t. Why twice t? Because you have got one thickness in here and one thickness over there. So the width here would be, this width is b minus twice t. Similarly, the height would be h minus twice t. So if you deduct that second moment of area of the inner, then you could get for the box section. Do remind yourself that we are taking away a smaller rectangle from a bigger rectangle, but the axis for those must be the same. So for the bigger rectangle, bh cube over 12, x is here, and also for the smaller rectangle, this axis is the same. If this was different axis for these two, then this method of subtraction will not work. This is a bit of a conceptual problem here. We have given 4 cross sections, and we have said that all of them has got the same cross sectional area. We have to find out which has got the highest second moment of area about the axis xx. Now we know second moment of area will be higher if the area is as far away from the neutral axis as possible. So the more area is away from the neutral axis, or the axis from which you are calculating second moment of area, then that has got a higher second moment of area. So we know that second moment of area's formula is area times the distance square. So the distance being distance from the axis. So if we look at, let's say, compare two. Say, let's compare in here. Say the first cross section has got thickness T, thickness T, thickness 2T. So they are virtually the same. A and B are virtually the same. And if you compare that with the section D over here, it has got a thin part, only one of these. Say if you compare A and D, then we could see only one of those wave, these vertical member are called wave. One of these wave is in there. The other wave is probably added to this flange. So these things are called flange. So this more area has been added to the further away from the neutral axis. So technically A and B are possibly of the same one. Only thing is that this 2T thickness has been separated into two thicknesses, two waves of T thickness. So there is virtually not much difference between A and B. But D is definitely higher than either A or B. Now what about C? Now C, we could see that much more area is concentrated around the neutral axis. So it is wasting quite a bit of an area which would have contributed much more if they are further away from the neutral axis. So possibly C is the lowest I value of all these four cross section. So if you have to rank, possibly I would say, without doing any calculation, this would be the top highest, followed by these two in the joint second, and then this would probably be the third. So in this case, the cross section is shown for the beam. So the beam might look like something going along these directions like this way. So you are applying a hogging bending moment, that is, it is shown in here. So what is a hogging bending moment? So if you have got the beam section is like this, a hogging moment would be something like this. So this is hogging moment. So the hogging moment will bend this beam in this manner. So if you remember the sponges and those other things that we used in the class, you will see the top bit then will be under tension and the bottom side would be under compression. Now the way this stress, the compressive stress and strain always vary linearly, always will vary linearly. So there is a moment, so it is not this one definitely, because it shows there is no strain is in there. So, and also this is not possible because it shows the square distribution. So either this or this. Okay. Now tensile strain is shown positive in this case. It is shown. So in this case we see the tension at the top. So tension at the top in there. In this case it shows tension at the negative over here. So our correct diagram of strain should be this one. And I don't think this is the correct way of drawing. Possibly it should have been much better if it is drawn like this. So if I have to draw this again, possibly I would draw it something like this. Something like this is a strain diagram. So the bottom bit is under compression, top bit is under tension. So this is the correct diagram. So first of all, you have to find out what is the nature of bending moment at cross section A. So if I isolate this part over here and we have got a load at this point. So what do you think of the bending moment at this cross section A would be? So the bending moment at this point would be like this. So this moment would be such that that resists this effect of this load. So the bending moment has to be in this direction. So bending moment like this is nothing but what in the past, just previous problem we said is a hogging moment. So these moment are hogging moment. So due to this, the beam would deflect in this way. So you have got tension at the top and compression at the bottom. So, and as we have said, always the stress or strain will vary linearly with zero strain at the neutral axis, and it will increase towards the top or bottom part. So what we are saying is stress or strain will always vary linear way. Okay, and zero strain at the neutral axis. So this is not right. Similarly, this is also not right. So either these two. Now it says the tensile strain as shown positive. So top part is tension. So this is right, and bottom bit is compression. So this is the correct answer. In this case again, we need to draw what would be the bending moment at this part. So as you could see, there are no loads acting onto this section. So the bending moment is really zero at this point. So bending moment at that section M is equal to 0. So that means there would be no strain will be applied, stress would be applied in the cross section. So if there is no moment, there is no bending stress. So M equal to 0 means no bending stress. So which diagram will reflect that? Of course, only one of is in here, which is this case. So this is the correct answer. For this problem, you may have been given some value of moment, numerical value of moment in kilonewton meter, and you have to find what is the magnitude of the maximum bending stress. And do take care of the term here magnitude, because I'm not talking about here whether that is tension or compression. Tension being positive, you could say higher than negative compression. I'm here asking what is the maximum numerical value of the bending stress. So if compressive stress in magnitude higher, then you should choose that. And then you have given some value of I, second moment of area, and the height of the cross section. Provide your answer in MPa. So you have to take care of the unit here. So if you do all the calculation in Newton and millimeter, then possibly it would be useful that you'll get the answer in MPa or Newton per millimeter square. So what I'll do is first I will convert that moment and which is given in kilonewton meter by 10 to the power 6. So because 10 to the power 3 would make from kilonewton to Newton, another 10 to the power 3 would make from meter to millimeter. So this much moment I need to convert that into Newton millimeter. And what is the formula for bending stress? Bending stress formula is divided by I, which is second moment of area, which is given already in millimeter to the power 4. So that's given, times the maximum distance from the neutral axis. Now this is the neutral axis X. So the maximum distance of the cross section from this neutral axis is either at the top or at the bottom, because both are the same. So this is H over 2. H over 2. So multiply by H over 2. So that H is already given in millimeter. So this would give you the value of bending stress. Okay, now let's approach this problem in a step-by-step manner. First, we will try to find out the expression of shear force, and we will take into account the sign convention that is shown on the right hand side over here. So we'll take a section from the left hand side at a distance x over here. Let's say we take a section over here. So we have got this bit of the beam there, and you have got a load of 7 kilonewton. So the shear force at this section would be going downward. Okay, so if this goes downward on the right hand side of the section, then that is a negative shear force. So let's write it down. So V is equal to minus 7 to start with. Now let's move a little bit further and take our next section over here. So what we mean is that this distance is now x. So our beam segment now looks something like this, where we have got a load of 7 kilonewton over here, and we have got a load at this point as 10 kilonewton. So our expressions for due to this 10 kilonewton would be, so we know already this is 7 kilonewton is represented in the expressions already. Now 10 kilonewton is going downward, so that means according to this convention that's a positive shear, so we'll write as 10 kilonewton. Now do remember that this expression that I'm writing is valid for any x. Now here, when the x was less than 3 meter, 10 kilonewton will not come into the expression of this shear force. 10 kilonewton only come in the picture when x is more than equal to 3 meter. So we need to use Macaulay bracket in here. So that means this would be, the second term would be only be available only when x is more than 3 meter. Now having said that, this gives a multiplication sign when x is, let's say, 4 meter, then that will give you, the Macaulay bracket would be 4 minus 3, 1 times 10 is fine, that as a shear force. But when say x equal to 5 meter, then that the Macaulay bracket will give 2. So 2 times 10 is 20. That's not shear force component or contribution due to 10 kilonewton. The shear force contribution at this point would still be, so if we calculate V at this point, V would be minus 7 plus 10. Okay, V would be minus 7 plus 10 at this point anyway. So this we can avoid by this multiplication by putting a power of 0 here. So even when say x equal to 5, say, then 5 minus 3 is 2, so x minus 3 to the power 0 would be still 2 to the power 0 is 1. So when multiplied with 10, that would still give you the value of 10 as shear force contribution from that 10 kilonewton load. Now let's move slightly further down. So if I add here now, we have got 12 kilonewton meter moment there. Now this is a moment, not really a force, so that will not alter the expression of the shear force. Shear force is the summations of the vertical forces, so that is 7 and 10. So that is 7 and 10 would still valid. 12 kilonewton meter moment will not contribute to the shear force at that location. Next, move slightly further down, and let's say my x coordinate is at this distance. So this is my new x. So if I draw the beam now, what we have got? We have got the force wise, I have got 7 kilonewton there. I have got 10 kilonewton here, which is covered by these two following expressions here, 7 and 10 times x minus 3. So these both are valid. Second expression is valid when x is more than 3, which is now. So these two are valid. but also I have got a load of 2 kilonewton per meter started to appear from x equal to, so this distance is 336 plus 4, 10 meter. So when x is beyond 10 meter, I started to have these loads of 2 kilonewton per meter. So this distance is here is x minus 10. So what would be the total load? 2 times x minus 10. Now using Macaulay bracket, we need to use, instead of a normal bracket, we need to use x minus 10 Macaulay bracket, because this value would be only be available towards the shear force when x is greater than or equal to 10 meter. So what I need to write, 2 times x minus 10. So that is because x is valid from more than 10. Now here multiplication of 2 and x minus 10 gives you the shear force, unlike the 10 kilonewton force which was here, that was the force itself, but the UDL is 2 kilonewton per meter. So you need to multiply with the meter here, how many meters this 2 kilonewton per meter load is acting, x minus 10 meter. So you need to multiply that with 2 to get the total load that would be going towards the shear force. So this, we are not going to use a power of 0 in this case, because both the terms are required to calculate the shear force, because 2 is really kilonewton per meter and x minus 10 is the length or over which this 2 kilonewton per moment per meter load acts. What would be the direction, plus or minus? This is acting downward, it's the left of the cross section, downward is positive, so I put as a positive sign. Finally, if we take the sections over here at a distance x, then a final load of 19 kilonewton starts to act, and that is going positive to the that is acting upward at the left of the cross section, so that will be with the negative sign, minus 19, because this is the left of the cross section, the force is going upward, which is opposite sign of the one which we have chosen, so that's why minus 19. And this 19 value would come into the expression of shear force when x is more than this distance, which is 6 plus 8, 14 meter. So when x is more than 14 meter, then only this last term would come into the expression. So we use Macaulay bracket, and as before with all other point loads, for the shear force we are not multiplying the distance with the load, so this should be to the power 0. So you could see first one minus 7 doesn't appear with any distance because we started from this point, so 7 is appropriately valid whatever value of x is. Second term is valid only for x greater than 3. Now that it's the load itself is 10, so although it shows like a multiplication sign, we used to the power 0. Third term is valid for x greater than 10, x greater than equal to 10 meter, and then the actual shear force is 2 times the distance, and finally here is 19 times x minus 14 to the power 10 as just mentioned. Now let's look at the expressions of bending moment. So let me take a section at a distance x from the left hand side as before. So let's say this distance is x. Okay. Now let me draw this segment of the beam here, and we have got a force of 7 kilonewton, reaction force from the support goes upward that direction. So what would be the bending moment at this section x? Now, of course, that would be required to resist this load the moment due to this load. So this should act anti-clockwise in this way, and this should be 7 times x. So if I want to now write down the moment expression, so the moment expression would be 7 times x. What would be the sign? Now this 7 times x is what is so-called sagging moment, but it is, our sign convention is opposite to that. If you consider the right hand side moment, this is opposite to this moment, so we replace 7x with minus 7x. Let's next take a sections over here, which is this distance is say x. So how does our moment expression should look like? So we have got 7 kilonewton there, and we have got 10 kilonewton over here. 10 kilonewton over here. So the contributions of moment due to 10 kilonewton would be in this way, because 10 kilonewton will try to rotate the beam in the anti-clockwise directions, so that must be registered at this section by a 10 kilonewton moment going in the clockwise direction. So what would be the value of that moment? That would be 10 times this distance. So what is this distance? So this distance is nothing but x minus 3 meter. So the moment would be 10 times x minus 3 meter. That would be the moment that would be created at these cross sections over here due to the 10 kilonewton load. Now as we are having a general expressions, this x is only valid for x greater than 3. So what I mean is, if our section was at this position, then 10 kilonewton load will not come into picture to calculate the moment, because we are only considering this bit. Only when x is more than 3 meter, say let's say here, then only this 10 kilonewton load will come into picture. So we need to replace this x minus 3 with Macaulay bracket. So as we've discussed, this is plus 10 times x minus 3. So that is the contributions of the moment due to this 10 kilonewton force. Now let's take our next section over here. So what we mean is this distance is x meter. Now we did look into account, so what is our beam segment now? So this is our beam segment. We have got 7 kilonewton load going upward at the left. We have got 10 kilonewton load going downward at this position. So those both of which has been taken into account here and there, but we have got a new moment. So this is a new candidate at 12 kilonewton meter moment acting at a distance 6 meter. So this is the third one, is the new that we need to add into our expression. Now as it is directly a moment, so we just don't need to multiply with any distance or anything. So it will be just added as 12 with our expression. And let's check the sign. So this is a sagging moment. Our convention hogging moment is positive, so that will come with a negative sign. But if we just leave it here 12 minus 12, that means it is valid for any x. So that means, okay, when x is less than 3, 12 would be still there. When x is say 5 meter, then 12 is still there. So we need to correct that. So we can use a Macaulay bracket saying 12 with x minus 6. That this third term only come into picture when x is more than equal to 6 meter. But that also creates a problem, because that means it is multiplication of a distance with the moment which is not true because 12 is already a moment, it's not a load. So we can avoid that by using what we did with the shear force as before with 10 kilonewton load. So we apply a power of 0 at the top. So that means whatever the value of x beyond 6 is, that would be 1, the content within the macula bracket. So the moment would be 12 when x is more than equal to 6 meter. So let's take another section over here now at x which is beyond 10 meter. So we have got 3 load component, 2 direct load and moment that we considered before. But for x more than 10 meter, we have started to get these loading UDL, which is 2 kilonewton per meter. And this distance is really how much? X minus 10. So the moment due to this 2 kilonewton per meter loading at this section over here. So what would be the moment? So moment would be load times the distance. So that is 2 times x minus 10. So that is the total load, and that will act at a distance x minus 10 over 2. So times x minus 10 over 2. So you'll get 2, these 2 you can get cancelled. So you can say x minus 10 square. Okay. So how did you get? 2 is the load intensity times x minus 10. So that is the total load, and that is acting at a distance x minus 10 over 2 from this cross section over here where you want to calculate moment. So that is x minus 10 over minus 10 square, and whether it is positive or negative, of course it is going to create a hogging moment, so that is with a positive sign. But do remember, as before, this is not a normal bracket we are going to use, because this expression will be only valid when x is more than 10 meter. So, or in other words, when x is beyond this line, then only this load will start to come into picture. So we are going to write that as plus x minus 10 square. So that means this fourth term would only be valid when x is more than 10. Finally, let's take a section at x beyond 14 meter. Then the other load 19 kilonewton will come into the expression. So the moment due to that would be 19 times x minus 14. Now, of course, using the macula's bracket, so that would be x minus 14. So this term means that it is only valid when x is more than 14 meter. Now, what would be the sign conventions for this? It is going to create a sagging moment, so that is with a negative sign at that point. So minus 19 times x minus 14. So let me just do it a little bit tidy way. So these are the expressions of shear force and bending moment. Make sure that you revise this properly and understand each and every term here carefully. And the final one is, what are the boundary conditions? Now we know first condition is when the beam deflects, whatever way it deflects, we know the displacement at this point is at point 1. So at x equal to 0, I have got displacement is 0. That is one boundary condition that we know. The second boundary condition I can write is over the other support point. So at point 2, at x is equal to 14 meter, y is equal to 0. So these two will be the known boundary conditions.